Welcome to Chapter 8, Met 1010, Air Masses, Fronts, and the Mid-Latitude Cyclones. So we have talked about air masses. We're now going to detail and classify our air masses. We've also talked about fronts, but now we're also going to classify and detail our fronts. And we're going to talk about how mid-latitude cyclones form, what causes them to form, and more importantly, how they are connected to the upper levels of the atmosphere and how the upper level processes develop, create, and then eventually dissipate mid-latitude cyclones. An air mass is going to be a very large body of air with homogeneous properties, homogeneous meaning the same, properties of temperature and humidity in any direction or also at any altitude. Now, air masses can come in dry, they can come in humid, they can come in cold, they can come in warm, and they can come in very cold, and any sort of combination of temperature and humidity. The source regions from air masses, where air masses develop, are typically flat or fairly flat with uniform composition, meaning not half ocean and half land, but uniform composition, fairly flat, light winds, and typically dominated by high pressure. And dominated by high pressure because air sinks in high pressure, and that sinking air keeps the air in contact with the surface, allowing the air to acquire the temperature and moisture characteristics of the surface. And so the classification of air masses, continental and maritime, referring to dry air masses with continental, and maritime air masses with moist or humid. And then we have Arctic, polar, and tropical. Arctic being very cold, polar being cold, and tropical considered to be warm. Here is a surface weather map of the continental United States showing a very, very cold air mass stretching across the entire eastern United States. And you can see the boundary between where the very cold air lies and what may be more moderate is going to be the front range of the Rockies. So this high pressure is centered over Mississippi. The cold air stretches from the Hudson Bay all the way down into the Gulf of Mexico. The station plots, the circles that you see on the map, the top number being the temperature, the bottom number being the dew point. And you can see that as far south as North Florida, 27-degree temperature with 18-degree dew point, cold and quite dry. But when you start getting up into places like Minnesota or Canada, we're seeing 15-degree temperatures with minus 32-degree dew point, so very, very cold air. So this is a massive air mass that's setting up over the entire eastern section of North America, and its source region, being cold and dry, is going to be the Arctic regions. So once an air mass is created, and you can see the continental Arctic, or the dry, very cold air, is created up over the Arctic, and the continental polar, the dry polar air, cold air, is created over northern parts of Canada. The maritime polar air, that cold, moist air over the northern Atlantic and northern Pacific, maritime tropical air over the southern Pacific, and also the southeastern or the southwestern Atlantic, and also the Gulf of Mexico, and then very unusual continental tropical air. So we're talking about dry, warm air, summertime only in the desert Southwest. Those are the individual source regions for those types of air masses. And after an air mass spends enough time over its source region to take on its specific characteristics, then it begins to move as upper level winds put the air into motion. So when a cold air mass moves over a warm surface, that very, very cold continental polar air from Canada moves south into the southeastern states, it is warm from below, and when you warm from below, you destabilize the atmosphere. Whereas when a warm air mass moves over a colder surface, where that maritime tropical air across the Gulf of Mexico or southwest Atlantic pushes north into the mid-Atlantic or even the Great Lakes or upper Midwest, then it is cooled from below, and that produces a stable air mass. Continental air masses are the continental polar, CP, or the continental Arctic air masses, both dry, and of course the Arctic very cold, the polar cold. They, as you might expect, originate over ice and snow. They are cold, dry, and very stable, and under the influence of upper winds, continental polar or continental Arctic air masses move south as areas of high pressure. Sinking air above the high pressure warms due to compression, and an inversion forms, meaning as that air in that dome sinks in the upper levels, it warms. So typically you've got that warmer air aloft, and that creates that inversion or that very stable air. Summertime, continental polar air from Canada, typically not as cold, but it also holds a lot more moisture. Here is another example of a massive cold air mass. This was a continental Arctic air mass originating over the Arctic regions. Actually happened back in 1984. This is known as the Siberian Express, and sometimes in Texas they refer to these as blue northers. In Dallas, folks will say that there's nothing between Texas and the North Pole but barbed wire fences, because North America is very flat, the plains in that region, so there's not a lot to block that cold air from sliding south. As we said in the previous slide, whenever continental polar or continental Arctic cold, dry air moves over a warmer surface, that destabilizes the atmosphere, creates an unstable environment. You have warmth at the surface, cold air aloft. That warm air is more readily able to rise. So an interesting thing happens when that cold Arctic or cold polar air moves over warmer waters. And when we say warmer waters, we're not necessarily meaning warm water, but relatively warmer, such as very, very cold air coming in out of Canada, moving over the Great Lakes. The cold air may be below zero. The water of the Great Lakes may be above zero. So relatively, it's warmer. And this creates what's known as the lake effect snow machine. So cold continental polar air moves over the warm waters of the Great Lake, or Great Lakes. The air mass is warmed from below, making that air mass unstable. Upward vertical motion pulls the moisture up and off the lake. As that warmer, moist air rises, it cools by expansion until the temperature of the air reaches the dew point, or 100% relative humidity, or saturation. Further lifting creates condensation and cloud formation, and eventually you'll get precipitation, and in those colder areas, it's going to come in the form of snow. So as the strong winds blow out of Canada from the northwest over the Great Lakes, you can see that the leeward sides of all the Great Lakes, the southeast and eastern sides, is where the lake effect snow machine dumps significant snowfall. And as we've seen in recent winters, you can get 6, 8, 10 feet of snow in a day in one region, where just a few miles away from the lake effect snow, you don't get any snowfall at all. When maritime polar air, which is going to be a cold but moist air, this has a source region over, let's say, the North Pacific Ocean or the North Atlantic Ocean, it comes in the form of cool, moist, and conditionally stable or conditionally unstable weather, meaning the environment of the maritime polar air mass tends to be conditionally unstable, where it's stable in the lowest levels, but then becomes unstable as you move up in the atmosphere. Air at the surface is warmer than the air aloft, and again, that means a little bit of upward motion. As the air moves inland, orographic lift or lift over topography lifts the moist air and produces snowfall. And then once inland, the air mass loses its moisture and brings fair and cool weather to the interior parts of North America. So your bottom illustration shows that maritime polar air, cool moist air coming in off of the Atlantic. The coastal range in Washington and Oregon is the Olympic Mountains. So as it goes up the mountains, orographic lift creates condensation and rainfall. As it comes back down the mountain, again, that air warms back up at the dry adiabatic lapse rate, back up the Cascade Mountains, more rain, and then we dry it back out again going down the leeward side of the Cascade Mountains. So on both the Olympic and the Cascade Mountains, some of that moisture is robbed from that MP air. So as it finally gets up and over the Rockies, what comes down on the east side of the Rockies, the lee side of the Rockies, the front range of the Rockies, is that modified, much drier Pacific air. Things are a little bit different with the maritime polar air that has a source region over the North Atlantic. Again, we're talking about fairly cold, fairly chilly, damp air, and the North Atlantic is going to be colder than Pacific air, and due to the westerly winds, you don't see a lot of that cold, damp air moving toward the northeast coastline of the United States. But occasionally you'll get a big dome, big Arctic high, big polar high will settle in over eastern Canada, and the clockwise flow around it will create a northeast wind that blows that cold, damp air toward the northeast and New England mid-Atlantic states. At the same time, typically, the Bermuda high pressure, that clockwise flow down across the south and western Atlantic, is creating a southerly flow across the southeast of warm air, warm moist air, that maritime tropical air. And where those two meet or converge, convergence at the surface is low pressure, and when it's elongated, that elongated area of low pressure will be a stationary front. So high pressure forces maritime polar air onshore in a northeast flow. Stationary front separates that maritime polar air from the maritime tropical air, and north of the front you tend to get stratiform or stratus clouds, showery precipitation, snow and drizzle. So what's happening is that warm moist air from the southeast is riding up and over the cold, damp air. So there's a temperature difference. They're both humid, but there's a temperature difference, the cold air being more dense, the warm air being less dense. So that warm air from the south rides up and over the colder air, and that upward motion creates the clouds and eventually showers. And this is one of the ways that we get nor'easters across the eastern seaboard. Not the only way, but one of the ways we get nor'easters. Now, maritime tropical air, pretty straightforward. That's going to be that warm, moist air in the South Pacific and Southwest Atlantic, the air mass that we largely deal with here in the Southeast and certainly Central Florida. But there's also this very unusual continental tropical. So continental referring to dry and tropical referring to warm. Those dry, warm air masses only happen in the summertime, and they originate in the high plateaus of the desert Southwest, particularly the Mexican plateau that we see across the southwestern part of North America. So hot, dry air originating in northern Mexico and the southwest United States creates a continental tropical air mass, lots of hot weather, lots of dry weather, and clear weather. The other side of that coin is going to be the maritime tropical air mass. Now, in our top right illustration, we can see that maritime tropical air mass covering all the southeastern states and being pushed north on up into the northeastern states as well. And so maritime tropical air masses, typically known as subtropical, are very warm, very moist. The Bermuda high pressure is what basically provides that very warm, moist air mass across the southeastern states. And again, as it moves north behind a warm front, that warmer, moister air will ride up and over the colder air and create stratiform, showery types of precipitation. Now, in 2012, we had a blocked weather pattern, and a lot was going on because of that. So looking at this, generally this is a surface map with an overlay of upper level winds. Not very detailed, but that purple arrow will be the upper level winds. And you can see that across a big chunk of the western half of the country, there was a deep and digging upper level trough of low pressure. And then on the eastern half of the country, out into the western Atlantic, a very large dome of high pressure. Well, the combination of those two large pressure patterns created what's known as a blocking flow, which means this upper level wind flow, that purple arrow that was blowing in the upper levels of the atmosphere above 500 millibars, was pretty consistent, and it went on for weeks, literally, several weeks, maybe 6 to 8 weeks. And what it created was a situation where the trough of low pressure dragged cool Pacific air down, so that maritime polar air got pulled off the North Pacific into the Pacific Northwest, where it produced some precipitation, but then dried as it moved inland, creating a very cool and dry scenario for the Rockies and the desert Southwest, until you got basically into California, and for the upper Midwestern states and the Dakotas. But that digging area of low pressure and the trough of low pressure in the upper levels induced what was essentially a semi-permanent area of low pressure at the surface, and the counterclockwise flow around that low, as you can see, that south wind off the Gulf of Mexico and the western Atlantic just pumped up very warm maritime tropical air, and we got a tremendous flooding in some cases across the region, but more importantly, some very, very hot conditions. And in the month of March in 2012, there were 7,000 separate record high temperatures in the United States. With an understanding of our air masses, whether it's a very cold and dry air mass or a very warm and moist air mass or even a cool and moist air mass, and the understanding that those air masses move with upper level winds, we also can see that you're going to have air masses bumping into one another, and literally air masses riding up and over one another, where more dense air masses will stick to the surface and less dense air masses will ride up and over the denser air masses. And the transition zones between those air masses, those are our weather fronts. Our cold fronts, our warm fronts, our stationary fronts, and our occluded fronts are all transition zones between air masses. So a front, as we have defined numerous times in this class, is a transition zone between two air masses of different densities and are known as elongated areas of low pressure. So areas of convergence. Upward motion occurs over fronts. Typically, it is temperature differences that define the front, such as a cold front or a warm front. But sometimes fronts separate air masses of only different humidity. I mean, the temperatures are about the same. There's just a humidity difference over an area, and that's what the front separates. Fronts have both horizontal and vertical extent. Meaning, looking at the surface weather map with our mid-latitude cyclone over the Great Lakes, an occluded front extending south, a cold front, then a warm front, and even a stationary front well back to the west. This is a surface weather map, and this gives you the illusion that fronts occur at the surface. But fronts not only have their horizontal extent that you can see, the elongated area of low pressure, but they also have vertical extent. They go up in the atmosphere. So fronts separate the 5 air masses from one another and are zones of lower pressure. They're troughs of low pressure. Fronts are classified as to which type of air mass, cold or warm, is replacing the other. For example, a cold front shows the leading edge of cold air displacing warmer air. And if you look at the front, you have a line, whether a red line or a blue line or a purple line, and then you have these funny shapes, triangles on the cold fronts and little half circles on the warm fronts. Those triangles are known as barbs, and the half circles are known as pips. And the direction that either the pip or the barb is moving is the direction the front's moving. So if we look back at our surface weather map, our warm front is moving from the southwest to the northeast, just basically on top of that area of high pressure with that clockwise flow around the high pressure, pushing that wind to the north from the south and southwest, and it's moving off toward the northeast. So our pips on our warm front are showing the front moving to the northeast, whereas the cold front, the cold air is wrapping counterclockwise around our area of low pressure over the Great Lakes, and that cold front is bringing cold air from Canada around the high pressure over Canada with the clockwise flow, and then down into the southern states on the backside of the low pressure with the counterclockwise flow. And the pips on that cold front stretching from Kentucky back into the panhandle of Texas are showing the movement of that cold air south. Now, looking at that stationary front stretching from Montana back into Texas, it is alternating pips and barbs. So that's showing that that front's not moving, it's stationary. And you can see that the winds are blowing from the southeast on one side, the northwest on the other, and almost blowing parallel to one another, which is why the front is stationary. And essentially what you're seeing is 2 air masses, both polar, so both cold, but the one over the plains being a dry continental air mass, and the air mass over the Pacific Northwest being moist. And that's a good example where these cold fronts are not separating temperature differences, but separating humidity differences. So here is our cold front. 2 different depictions of the cold front. On the upper right, we just see one front with cold air, followed by a second front of very cold air. Both are moving from left to right, and we can see the pips on the fronts moving, showing that direction. And then out ahead of the polar front, that warm air is flowing up from the south. So a cold front is a transition zone in the atmosphere where an advancing cold, dry, stable air mass displaces a warm, moist, unstable air mass. And whenever you move cold air over warm air, so you take cold air, you move it over a warm surface, you warm that air at the surface, that destabilizes the atmosphere. And looking at that lower illustration, you can see the result of the unstable atmosphere creating clouds with vertical extent, our cumulus and our cumulonimbus clouds. So advancing cold fronts will have cloud cover well out ahead of the cold front. And you have very defined cloud patterns and precipitation patterns associated with cold fronts. This cold front at the surface is showing a southerly flow out ahead of it with 50-degree temperatures and a northwesterly flow behind the cold front with temperatures between 39 and 42 degrees, and even much colder as you go further off to the north and west. That warm, moist air is literally scooped up, almost bulldozed up by the denser cold air, and as it's lifted up, it cools by expansion until the temperature reaches the dew point, which in this case is 32 degrees. Once the temperature reaches the dew point, it has 100% relative humidity and saturation. Further lifting along that front creates condensation and cloud formation. Condensation is a warming process, further lifting those parcels. And again, that unstable atmosphere, you reach the level of free convection and you get these towering cumulus clouds, which along cold fronts can produce not only thunderstorms and heavy precipitation, but lightning and severe weather in the form of hail and potentially even tornadoes.
The cold front represents a boundary where cold air is replacing warm air. As the cold front moves along, warm air ahead of the front is lifted along the frontal boundary. The rising warm air often condenses into huge thunderstorms that produce heavy rain, strong gusty surface winds, and occasionally hail. As the cold front passes, the wind shifts, temperatures drop, and precipitation usually ends as drier air moves in behind the front.
We can determine the location of a cold front by cloud patterns, and we can determine the the location of a cold front based on precipitation patterns. As we see in the radar imagery to the bottom left, along and ahead of the cold front is where we find the showers and the thunderstorms with a little bit of lingering rain behind the front, but then very rapid clearing. And of course, that's going to result in a cloud pattern of towering cumulus clouds just along the front, out ahead of the front, high clouds, and then behind the front, clearing cloud cover. If you were looking for a cold front on a surface weather map, if the blue cold front had not been drawn, take a look at the surface weather map on the right. We're going to focus where the cold front crosses the Tennessee-Mississippi border. And we can see several things that happen between the areas to the south and to the north, the transition from the warm air to the cold air of the cold front. We have sharp temperature changes, sharp moisture changes, a wind shift, and pressure changes. So the two station plots we're looking at, northern Mississippi and then southwestern parts of Tennessee. And in northern Mississippi, the temperature is 50 degrees and the dew point is 48 degrees. So there's a very small dew point depression. The dew point's very close to the actual air temperature, and so we can see that it's relatively humid air, and there's lots of moisture there. The R with a little arrow underneath the 50, that represents thunderstorms. Of course, the circle filled in represents the cloud cover. And the most specific thing you can see with the frontal passage is the winds are from the south and west at about 15 knots. Just to the north, not very far away, in southwestern Tennessee, we have a 39-degree temperature. The precipitation is more just showery, but most specifically, the winds have shifted, clocked all the way around the north and west, and they've picked up to about 25 knots. Now, if you move further to the north and west, we're going to get up into northern parts of Arkansas. We can see where the temperature is even colder, and the dew points have dropped. The winds are there from the north and west as well. And then once you get way on up to the north, into areas like Missouri, you can see where the cloud cover has begun to clear, and we have a 24-degree temperature, a 17-degree dew point, so much colder, much drier air, and that northwest wind as well. Out ahead of the cold front over southern parts or central southern parts of Mississippi and Alabama, we have that southwest flow of warm, moist air, and behind the cold front, that northwest flow of cold, dry air, all part of the counterclockwise flow into the low that is the parent of this cold front. A warm front is the transition zone where advancing warm subtropical air from the south and moist air is replacing a retreating cold, dry polar air mass. So with a warm front, you have warm, moist subtropical air from the south, and it's moving forward to replace an area of cold air, cold, dry air, that's moving back to the north. And so the warm front typically is moving from southwest or from south to north. Out ahead of the cold front, to the north of the cold front, there's generally an easterly flow and colder air. To the south of the warm front, you're going to find that warm, moist air. The cloud and precipitation patterns are quite a bit different, but essentially you're going to see a similar type of transition from one side of the front in terms of wind shifts and also temperature and humidity gradients, or temperature and humidity differences. So if we look at the illustration to the left, the cloud formation and the precipitation is a function of what is known as overrunning. So think about the warm, moist air that's advancing and overtaking the cold, dry air. Warm, moist air will be less dense, so it will ride up and over that colder, drier air, and that's what is known as overrunning, as opposed to the cold front, in which the cold and dry air is replacing the warm, moist air, and that cold, dry air literally lifts that warm, moist air straight up. With the warm front, that warm, moist air of the advancing warm front is sliding up and over your cold air that is receding. And so when you have cold air at the surface and warmer air aloft, that is going to be a stable environment. That's a stable environment. The cold air, if lifted, will tend to be colder than the air above it and will want to sink back down to its original position. So what you get is those stratiform clouds. Stratus, the nimbostratus, where the rain then transitions into snowfall, and then just some high cirrus out ahead of it, and much, much colder air. So if you look from south to the left, to north to the right, you have that cold air that is receding. As that warm air approaches, the warm air rides up and over it, creating a stable environment. Flat stratus clouds, eventually those clouds get thick enough where they produce rainfall, then cold enough where they produce snowfall, and then way out ahead of it, you have that much colder air. If you look at the surface map to the right, we can see that behind the warm front is that typical south-southwest, maybe even southeast, warm, moist airflow. You can see the dew points and the temperatures in that region are quite, well, the dew points and the temperatures are higher, and you have a very low dew point depression indicating high relative humidities. And the winds from the wind barbs you can see are from the south and southwest. And then out ahead of the front, those winds shift to the south and southeast, and eventually, well north of the front, you can see them on the upper left, where we have some snowfall. Those winds are beginning to shift east, and eventually they'll shift to the north and east. So that wind shift is a very, very specific indication of a frontal passage. And remember, because the winds are moving in two different directions, those winds are converging at the surface, and that's also the lift that pushes that warm, moist air up and over the cold air, and how we get the warm, moist air at the surface to its dew point, to 100% relative humidity, to condensation, cloud formation, and eventually precipitation.
A warm front represents a boundary where warm air is replacing cold air. The clouds that form along the frontal boundary may extend far out ahead of where the front is touching the Earth's surface. In winter, as the cold front approaches, precipitation may begin as snow, which often changes to sleet or freezing rain, and finally to rain. As the warm front passes, temperatures rise, winds shift, and precipitation usually ends. In the warm air behind the front, scattered clouds often form.
Stationary fronts are when two separate air masses of different densities, so one could be cold and one could be warm, or it could just be humidity differences causing the density difference. Remember, more humid air is going to be less dense, drier air is going to be more dense, warm air will be less dense, cold air will be more dense. So frontal zones are transitions between air masses of different densities. So a stationary front is where those two air masses are not moving. They're just sort of rubbing up against each other. The winds will be coming from two different directions, so that frontal zone, that transition zone, that stationary front will be an area of low pressure, elongated area of low pressure, and will provide lift, and so lift will generate cloud formation and precipitation. But generally, the precipitation is much closer to what you would find over a warm front. So not quite stratiform, a little bit of vertical development, and maybe you'll have some thunder, but typically closer to what you'll get with a stationary front, more just that showery precipitation. Stationary fronts are then transition zones between two air masses that are not moving or are moving very slowly. So rarely is a stationary front dead stop. Typically it's sliding one direction or the other, or sometimes it's kind of moving back and forth, undulating slowly. These two air masses will sometimes interact along a stationary front, agitating the atmosphere, and that boundary will have some showers, even a thunderstorm, but generally there's not any warm air or cold air moving. The weather along these fronts is similar to warm fronts, less turbulent, sometimes even much, much longer lasting. You get a stationary front, it doesn't move, it can stick around for a couple of days, where a warm front typically is moving to the north. Now, we do see this in our fall and our spring seasons in central Florida, where cold fronts can advance all the way down the peninsula. They get stuck, and then you get a stationary front with some slightly denser air to the north, slightly less dense air to the south, and all the moisture of the Gulf and Atlantic just sort of providing showers. And that's when we get those gray days that may go on for 2 or 3 days. So there's no large-scale advancement of warmer or colder air. The stationary front is marked by alternating sections of red and blue, indicating, again, it's not moving in either direction. Sometimes a cold front, as I mentioned in Florida, or even in other parts of the globe, literally, a cold front can be marching along with cold air behind it and advancing to the south. And as that colder air warms, the further south it gets, the density differences become negligible, and that cold front will stop. And sometimes even stretch out and become elongated. And that's very typical when they transition, a cold front transitions into a warm front. And a cold front transitions into a stationary front. And sometimes warm fronts can transition into stationary fronts as well. Now, throughout the coursework, we have looked at cold fronts and warm fronts, and oftentimes when we've seen mid-latitude cyclones or extratropical cyclones, we've seen that purple front with both the pips and barbs moving in the same direction, but it's purple. And those fronts are known as occluded fronts. And occluded fronts are simply where faster moving cold front, or a faster moving cold front, catches up and overtakes a warm front. So it's where colder air catches up because of higher density and overtakes warmer air. And sometimes that warmer air is cool as well, but the bottom line is the colder air is colder. And again, it's a purple line with alternating pips and barbs. And there's generally two separate types of occluded fronts. And one is where very, very cold air lifts up slightly cooler air, because it's very, very cold air advancing, and it lifts up slightly cooler air. And that's going to be in a typical mid-latitude cyclone traveling across the country with the cold air coming in from the north and catching up to the warm front. There's another situation where we have more humid air, so it may not be quite as cold, and that cooler air catches up to a colder air mass, and then it's lifted up and over the front. And that occluded front is known as a warm type. So a cold occlusion occurs when the air behind the occluded front is colder than the air ahead of it. The cold occlusion acts in a similar way to a cold front in that the cold air behind the front undercuts the cool air ahead of it. Whereas a warm occlusion occurs when the air behind the occluded front is warmer than the air ahead of it. The warm occlusion acts in a similar way to a warm front in that the cool air behind the front is lighter than the cold air ahead of it, and this causes the cool air to pass over top of the cold air. So we're not going to necessarily focus on the nuances of cold type or warm type. What we want to understand is the general concept of an occluded front as being where the cold air has caught up to somewhat warmer air, and an occlusion occurs. And literally, the occlusion is where that warmer air is lifted up, and that's what creates the rainfall along it. So this is what an occluded front looks like from both the warm occlusion or the cold occlusion. Now, these illustrations are set up a little backward. The beginning point is at the bottom, and then at the top is the end of it. So at the very, very bottom is what it looks like on a surface map. So I'm going to start with that warm occlusion, where an extratropical or a mid-latitude cyclone comes on shore off the Pacific, and that cool Pacific air it creates the cold front, moves into a region of warmer air, but eventually the cold front catches up to the warm front, and the cool air then has to move up and over the colder air that we see inland from the Pacific Ocean. So that's the very bottom left illustration. That's the way it looks in the surface. And that purple line, of course, is the occlusion. So A, just above it, is that cooler air advancing, and possibly with showers and thunderstorms, because it's a typical cold front moving into warmer air, creating an unstable environment and clouds of vertical extent. At the same time, that warm front is moving out ahead of it, but more slowly, and it's creating that stable environment in the stratiform clouds and showery precipitation. And eventually that cold front, with the cool air behind it, catches up to the warm front, and that cooler air literally slides up and over that colder air, and that is the warm occlusion. And you sort of have a mixture of both thunderstorms and showery precipitation with that. On the right is our cold occlusion. Now, at the very, very bottom, that's the way it looks on your surface weather map. And again, a very typical mid-latitude or extratropical cyclone with your low, your cold front extending to the south and west, and warm front extending to the north, to the south and east, that is. And eventually that cold front near the low catches up to the warm front. And where the cold front catches up to the warm front, that's where the occlusion begins. And in this case, very cold air is catching up to colder air. Ahead of the warm front, there is cold air, but behind the cold front, it's very cold. And so if you look at A just above the surface map, we can see the very cold air marching along into that warm sector, and with cold air over warm, you get an unstable environment and clouds of vertical extent and thunderstorms. And then once that cold front literally catches up to the warm front, that is the initial occlusion. And one thing you need to recognize is at the initial occlusion, that is when this mid-latitude cyclone is at its most powerful. That's the deepest point of the cyclone and where it is strongest. So we can see at B, where at the initial occlusion, we have a mixture of thunderstorms and showers, and then as that very cold air undercuts that colder air, so density differences, very cold, more dense, cold, less dense, and lifts it up, you tend to get more showery precipitation, and that is your occlusion. we have talked a lot about the mid-latitude cyclone, also known as the extratropical cyclone, or sometimes middle-latitude cyclone. And in the text, they do refer to it as a wave cyclone as well. We've talked a lot about that, the combination of the low, the cold front, the warm front, and eventually as that cold front catches up to the warm front, our occluded front, the counterclockwise spin around that feature, the thunderstorms along and ahead of the cold front, the showery precipitation and snowfall out ahead of the warm front. But let's begin to detail how that actually develops, the life cycle of that particular weather feature, and then we're going to talk in detail how the upper levels of the atmosphere impact, enhance, and then weaken that mid-level cyclone, that mid-latitude cyclone. All right, so the polar front theory is essentially something that the Norwegians came up with in the 1920s. And we were beginning to understand the three-cell model at the time, and that at somewhere around 60 degrees north latitude, that polar front existed, separating the colder air from the cooler air to the south. And along that polar front, we had those polar easterlies, and we had the westerlies from the subtropical high. So the high pressure, if you look at A, the stationary front, the H represents that polar high. The H to the south of the front represents your subtropical high, and of course you see your wind flows. And so essentially, that is kind of a static situation, creating that polar front at about 50 to 60 degrees north latitude. Now, upper level disturbances, and we'll detail those in a moment, create cold air advection and warm air advection. And remember, advection is the horizontal movement of air. So cold air advection is that cold air moving from south to north across well, not across, but pushing south into that stationary front. And the warm air advection is that warm air, more humid air pushing north. And so as those air masses begin to move, we no longer have a stationary front, but we have a cold front and a warm front. Now, as that low itself begins to move as well, because the low only forms once that cold air advection forms, and as the low begins to move along, typically to the east, we can see that cold air wraps around and the warm air lifts north, the green shading in both B and C representing precipitation along those boundaries. And then as we take it down from a stationary front to a frontal wave to an open wave, so that open wave in C is the mid-latitude cyclone, in which there is a cold front and a warm front that are not connected. There's no occluded front. And so very important to understand that between that cold front and the warm front is the warm sector of the mid-latitude cyclone. That's where you find the warm sector, the south to southwest winds, the warm humid air of the mid-latitude cyclone. Now, at D, you still have a warm sector, but you also have the initial occlusion. That is where the cold front first catches up to the warm front. And at this point is when the mid-latitude cyclone is at its most intense because, and this is important, mid-latitude cyclones are provided their energy by temperature differences across horizontal differences. So where you have significant temperature differences, you're going to have a significantly deeper mid-latitude cyclone. And then where you have less temperature difference, you're going to have a weaker mid-latitude cyclone. So as that initial occlusion begins, that is where we find the mid-latitude cyclone at its most intense, in that mature stage. That's when it deepens the most. And you can see as we advance to E, where there's more isobars around that low, indicating a deeper low. And then eventually, as that moves off to the north and east, that low becomes cut off. It leaves a warm front, a stationary front behind, and you see the dissipation of that mid-latitude cyclone. So this is the very, very general life cycle of a mid-latitude cyclone. But again, a couple of things to remember. The energy is provided by the temperature differences. Colder and warmer air provide the energy for the mid-latitude cyclone. It does reach its mature state at the initial occlusion, and that begins the most intense portion of the mid-latitude cyclone. So we said that the mid-latitude cyclone begins when cold air advection begins. Remember in the previous slide, we had the stationary front with cold air to the north and warm air to the south. So what causes that cold air advection to develop at the surface? Well, what causes that is literally cold air advection in the upper levels of the atmosphere, or a trough of low pressure, a low pressure in the upper levels of the atmosphere representing colder air aloft, begins to move south. And in our left side of this illustration, we can see that developing trough of low pressure in the atmosphere. And you can see where the air parcels are moving into the trough, they are converging. They're getting closer together, just like the cars going around the Fairbanks curve in I-4. And as they get closer together, they're also going to slow down. And that is your convergence. They come together, they converge. And since that is the top of the atmosphere, the air can't go up, so it goes down. That creates sinking air and high pressure at the surface. And then in the exit region of that trough, that is where there's divergence aloft. And that divergence, air is being evacuated. It's being moved away. It can't be replaced from above, so it's replaced from below, creating air that is rising off the surface. And that rising air off the surface is what creates the counterclockwise turn of the low pressure at the surface and that cold air advection. So the upper levels of the atmosphere initiate the low at the surface. So convergence and divergent patterns aloft are extremely important to the development of mid-latitude cyclones. Diverging air deepens cyclones. So on the right side, it's diverging air, that air moving away where it says DIV, deepens that cyclone at the surface. And then on the left side where it says converging air, that builds an anticyclone, or an anticyclone is created. So convergence is where air piles up, net inflow to a region, and divergence is where air spreads out, net outflow from a region. So convergence and divergence can also occur when winds slow down or when winds speed up, or when those contour lines converge or diverge. And so the chart on the right is just a very, very similar situation, just a more simplified view with the upper level trough creating the cold air advection at the surface, because as the air sinks in the entrance region of the trough, the sinking air spreads out and turns right, creating that northwest flow. And as the air diverges in the upper levels of the atmosphere, the rising air creates counterclockwise flow and that north to northwest flow around the low. And that's what gets that cold air going. And so we go from a low at the surface to a low with a cold front and a warm front, our open wave, with the warm air being the warm sector, and that is your mid-latitude cyclone. So it takes a trough of low pressure, or at the very least, divergence in the upper levels of the atmosphere to induce the high. The divergence induces the low at the surface, and the convergence in the upper levels of the atmosphere inducing the high at the surface. So those waves in the upper levels of the atmosphere, both these illustrations at the bottom are showing the 500 millibar level, so that's above that level of the upper levels of the atmosphere. Those waves, whether they're troughs that we were looking at in the previous slide or even ridges, those are called long waves. And when you go from one trough to the next, or from one ridge to the next, that is one long wave in the atmosphere. So upper level winds flow from west to east, and they are known as the upper level westerlies. A zonal flow is nearly due west to east, while a meridional flow has a north to south component to the wind direction. Waves that develop in the westerlies allow for the transport of cold air south and warm air to the north. Those long waves have a length of many thousands of miles, the wavelength, from trough to trough or from ridge to ridge, crest to crest, and move quite slowly. Now, embedded in the long waves are these little short waves, or just disturbances, and they move more quickly, but they also move within the long wave pattern. And as that little short wave, and you can see that in the illustration in the left, as those short waves move to the long wave pattern, they tend to deepen troughs, making the troughs dig deeper, and you can see that from day 1 to day 2, where that short wave way out over the Pacific digs into a trough, and by day 2 we get a nice deep trough over the west coast of the United States. And then also, as those short waves move into ridges, they tend to weaken. So short waves move into troughs, and they deepen the long wave trough. Short waves move into ridges, and the short waves themselves weaken. Now look at day 1 and day 2 with short wave number 3, the one over on the east coast. As it's moving into the long wave trough, it's not very big, and then as it digs into that long wave trough, not only does it intensify, but it also deepens that trough. And the reason why we have the isotherms on day 2, the 10 degree, 20 degree, 25, and 30 degree below zero red dashed lines, those isotherms, are to show how those upper level winds cross the isotherms as those lows deepen, meaning a north wind is now going to push that cold air to the south on the entrance region of the trough, And then on the exit region of the trough, that warm air is going to push that southerly flow is going to push that warm air to the north. And that is how we get the cold air and warm air advection in the upper levels, forcing the cold air and warm air advection in the surface. In addition to the long wave troughs and ridges in the atmosphere that provide directional convergence and divergence, with the convergence in the upper levels happening in the entrance regions of the trough and the divergence in the upper levels happening in the exit regions of the trough, we also have these cores of faster moving winds within the westerlies. And those westerlies are the jet streams, and the cores of faster moving winds are known as the jet streaks. So the jet stream helps to deepen cyclones with the divergence aloft and build anticyclones with convergence aloft. And where the air converges on the surface, you get the anticyclone. Where the air diverges in the upper levels of the surface, you get the cyclone. But within the jet stream is a core of stronger winds known as the jet streak. And in this particular illustration on the left, now where the winds are speeding up in that jet streak, that area of maximum winds, also happens to be in the exit region of that trough. And that literally enhances that lift, because not only do you have directional divergence in the exit region of that trough, but you also have speed divergence, where winds are going from slower speeds to much faster speeds. And so air converges at point C in the entrance sector, forcing cold air to sink and the high at the surface to build, so the anticyclone at the surface to build. And then air diverges over point D in the exit sector of the jet streak, causing air to be pulled up off the surface and deepening that low, or deepening that cyclone at the surface. And so you can see with this right-hand illustration, just your typical trough in the upper levels of the jet stream, and a couple of things happening. Yes, the convergence and divergence creating the surface high and low, but then look at the low from day 1 to day 2. Over Michigan on day 1, but then moving into northwestern parts of Canada as we move into day 2. That low, that mid-latitude cyclone, is following the direction of the jet stream itself, that long wave trough. It's following that same direction and at about half the speed of that long wave trough. And you can see from day 1, an open cyclone, to day 2, where it is at its occlusion and has moved through the deepest point of that cyclone, where now the occlusion is occurring and cold air is lifting the warm air up. And so you don't have as much of a temperature difference at the surface. Now you're getting into a weakening cyclone. So here again, a reiteration of our developing mid-latitude cyclone or extratropical cyclone. In A, we have a nearly zonal flow in the upper levels, lying almost parallel to our surface stationary front, which in this case would be our polar front. To the north of the polar front in A, we have the polar easterlies. To the south of the polar front in A, we have the westerlies at the surface, warm from the south, cold from the north. And our long wave pattern is nearly zonal in the upper levels of the atmosphere. Move to B, and in the upper levels of the atmosphere, now our long wave pattern, a trough has begun to develop. The reason why this trough has deepened is because the flow at B is disrupted by a short wave. Now, the short wave is not shown in this particular illustration, but a short wave moves into that trough, deepening that trough in the upper levels of the atmosphere. And again, north winds now cross over those isotherms, so they'll begin to push cold air south and lift warm air to the north. So the short wave induces that trough in the long wave pattern. Cold and warm air advection at the surface begin. That's cyclogenesis at the surface, or the beginning of the cyclone at the surface. Cyclogenesis, the development of the beginning of the cyclone. As that trough deepens in the upper levels due to the short wave, vertical motions in the atmosphere are produced, which are required for the extratropical of the wave cyclone to form. So those vertical motions are the downward air in the entrance region of the trough because of convergence at 1 in B, and then in B in the upper levels at 2, divergence aloft, creating the upward motion and enhancing our wave cyclone. And of course at C, you can see where the occlusion has begun, so now we're at the most intense portion of the cyclone. But in this situation specifically, our long wave pattern breaks down a little bit, and that upper level low forms. Now, with that upper level low directly over our surface low, we have convergence. Remember, low pressure at the surface is and aloft is convergence. So now, at 500 millibars, we have convergence and convergence at the surface. Well, that convergence in the upper levels is now going to begin to force air to sink, all right? And that is going to then weaken that cyclone. And so this is one way that weakens cyclones, as you get these upper level lows on top of them. If you move back to B, I want you to notice that the upper level low and the surface low are not vertically stacked. The upper level low, the actual purple L, is to the north and west of the surface cell. It's when this upper level low gets directly above the surface low that it causes it to weaken and fill in. So one last look at the combination of the 500 millibar levels, that upper level chart, and the surface chart. Winds aloft steer the movement of surface pressure systems. Cyclones move at about half the speed of the upper level 500 millibar flow. For a cyclone to deepen, it must have upper level support or an upper level counterpart. And that is the purple low, that upper trough, not directly over the low, but to the north and west of the low. That trough in the upper levels of the atmosphere provides that upper air support. It provides the divergence aloft required for that low at the surface to deepen. Cyclones deepen under the exit region of an upper level trough, while anticyclones build under the entrance region of that trough. Convergence aloft forces sinking air, and divergence at the surface and divergence aloft creates upward motion and convergence at the surface, or low pressure. And again, this is another chart showing you how that pattern develops and what we see at the surface. At the surface, with high pressure, cold air, and clear skies along the frontal boundary, we have showers and thunderstorms. Ahead of the warm front, we have precipitation and snow to the north and northwest of the warm front. You can look at the pressure pattern and see falling pressures ahead of the cold front and then rising pressure on the backside of the cold front. And again, out ahead of the warm front, the pressure is falling as well. And then behind the warm front, that pressure would increase until the cold front comes through. So you can see our precipitation patterns, our pressure patterns, and our wind patterns as they switch and change as a mid-latitude cyclone moves through. So this animation is a fairly long animation showing everything that we have been talking about. So if it hasn't started moving yet, you can go ahead and click that lower right-hand side. And you see high pressure or subtropical high to the south with that southwest warm airflow, the polar high to the north with that northwest cold airflow, and at the surface, the cold air advection creating the cold air behind the low and the warm air ahead of the low. And so that area of low pressure begins to form at the surface as in the upper levels, that low pressure begins to deepen, and the winds in the jet stream, we begin to see some degree, and there's that shortwave trough, and the winds in the jet stream begin to provide some divergence aloft to help intensify that low. You can see that also in the upper levels that the winds are currently crossing the isobars, where they are pushing cold air to the south, cold air advection, and then warm air to the north. Now, as that shortwave trough begins to transition and move, you can see the low at the surface is also moving with that long wave trough. And the low at the surface is moving at about half the speed as those upper level winds in the jet stream. And you can see the formation and development of the low at the surface, pretty typical open wave mid-latitude cyclone, cold air advection behind the low, warm air advection ahead of the low. So you have the warm sector of the mid-latitude cyclone, showers and thunderstorms along the cold front, showery precipitation out ahead of the warm front, and then to the north and northwest of the low, that is where we begin to see some snowfall. Here our occlusion begins, our cold front's catching up to the warm front. Here we are at the deepest, most intense part of the cyclone. But as that occlusion occurs, what's happening? Well, the colder air is lifting the warmer air ahead of it. And so around that occlusion and that low, now there's not as much of a temperature difference. And so that's why that cyclone begins to weaken. The temperature gradient is not nearly as significant. So eventually, as it progresses, the cyclone weakens and dissipates as it moves on off into the north and east. So this wraps up this lecture. The next lecture will be Chapter 9. And that will be on weather forecasting, not how to forecast the weather, but the different types of weather forecasting techniques that exist.